What will be the future fate of the universe? The universe, as we know, is expanding. As a result, there are two possibilities. Either the expansion will continue forever, or it will not. But which one is correct? For a long time, we thought we knew, or at least we believed we knew, what we needed to do to find out. At a certain point, however, things became more complicated. Why? Because a component of the universe entered the picture that we did not know existed: dark energy. In recent times, instead of decreasing, doubts have actually increased. Recently, new results were published from an experiment called DESI, which aims precisely to understand what dark energy is. The results seem to indicate that dark energy is not of the simplest type that we had hypothesized until now, namely the cosmological constant, an idea that dates back to Albert Einstein himself. It could be something different, and this would have very important consequences for the future fate of the universe. What did DESI observe? And what does it tell us about the future fate of the universe? Let us try to understand it. For a long time, scientists asked themselves this question, and after the discovery of the expansion of the universe, they thought they had found a way to solve it. There are two possibilities. Either the expansion will continue forever, or at some point it will stop and turn into a collapse. Understanding which of the two scenarios is correct seemed simple. We can imagine the expansion of the universe like throwing a stone upward. If we throw it with a certain speed, the stone rises to a certain height and then falls back down, if we are on a planet with gravity similar to Earth's. But if the planet had much weaker gravity, with the same launch speed, the stone might never come back down, and instead move away forever. With the universe, something similar was thought to happen. There is an expansion speed, given by the Hubble constant, and the future fate of the universe, in the traditional view, would depend on the total amount of matter present. If there were enough matter to slow the expansion until it stopped, the universe could collapse into a big crunch, a final collapse symmetrical to the Big Bang. If, instead, the matter were insufficient, the expansion would continue forever. In this second scenario, the universe would become increasingly empty and cold. Stars would switch off one after another, without new ones being born. The universe would become an ever darker, colder, and more desolate place, a depressing but eternal end. During the 20th century, scientists tried to take inventory of the matter present in the universe. It was discovered that visible matter, the kind that forms stars, represents only a small fraction of the total. There is also dark matter, invisible but possessing gravity. However, even by adding up all the estimated dark matter, there still did not seem to be enough matter to stop the expansion. This suggested that the universe was destined to expand forever. But at the end of the 20th century, things became even more complicated. It was discovered that the expansion of the universe was not only continuing, but accelerating. To explain this acceleration, an idea of Einstein was brought back: the cosmological constant. Einstein had introduced it at the beginning of the 20th century to make the universe static, convinced that it was not expanding. After the discovery of expansion, he called it the greatest mistake of his life. However, in 1998, two independent groups of astronomers discovered that the expansion was accelerating, and the cosmological constant suddenly became useful again. If the expansion accelerates, then the universe will continue to expand forever. For decades, this was the most widely accepted scenario. The problem is that we do not really know what dark energy is. There are many theoretical alternatives: modifying general relativity, introducing new models such as quintessence, or explaining the acceleration in different ways, such as in the timescape model. Quintessence hypothesizes a dark energy that changes over time. In this case, the universe could move from a phase of acceleration to a future phase of contraction. DESI, the Dark Energy Spectroscopic Instrument, is building a three-dimensional map of the universe by observing millions of galaxies. The data from 3 years of observations include about 15 million galaxies and cover up to 11 billion years of cosmic history. The results are compatible with the cosmological constant, but when combined with other observations, such as the cosmic microwave background, interesting discrepancies emerge. The data seem to favor a model of variable dark energy, more important in the past than it is today. If confirmed, this scenario could lead to a future collapse of the universe instead of eternal expansion. These results are not definitive. Further observations and new data are needed. The truth is that we still do not understand dark energy, and we may never fully understand it. Instruments such as DESI and Euclid will continue to collect data. The final fate of the universe may remain a mystery, but this is part of science, accepting uncertainty, improving models, and building increasingly precise instruments.